So Avogadro's number is an incomprehensibly large number. It has to be. It equals the number of particles in a mole of something. And in 2019, that was defined as exactly 6.02214076 times 10 to the 23rd particles. And as a chemistry teacher, I'm under a contractual obligation to love this number. I even got married on October 23rd, which is International Mole Day. I'm not kidding, I'm all in on Avogadro. Now, chemistry teachers love trying to use Avogadro's number in goofy conversions to show how big it is. But in the end, I don't think they're very helpful. There are lots of big numbers we could use in goofy conversions, and the story of Avogadro's number is so much more than the number itself. So if you really want to impress somebody with Avogadro's number, don't do conversions. Tell them stuff like this. Tell them that the scientific acceptance of atoms hinged on finding Avogadro's number. You see, starting back in ancient Greece, there were two camps when it came to the nature of matter. One camp, led by Aristotle, thought that matter was continuous, and you could continue to subdivide matter smaller and smaller onto infinity. The other camp, led by Democritus and friends, argued that you could only chop matter so far until it became uncuttable, atomos, as the Greeks called it. So for the next 2 millennia, the debate raged, but the atomists slowly started to pull ahead. Despite running up the score, Team Atom couldn't win the game. The problem was that no one could actually find an atom. What if atoms were so small that they were beyond experimental reach? To really establish atomic theory, scientists needed to find the absolute weight of atoms. And to do that, they needed Avogadro's number. Editorial note here, I'm going to stop using the term Avogadro's number for a while because this story starts at the beginning of the 19th century. And that honorary title would not be bestowed for another 100 years. So with that in mind, let's just call it secret number N for now. So if your friend isn't impressed yet, tell them that Avogadro's number was a powerful idea even before it was a number. In 1808, Dalton theorized that atoms of different elements had different and distinct relative weights. Dalton knew he couldn't find the actual absolute mass of atoms. They were much too small. But he had a hunch he could determine their relative masses, the mass of atoms compared to each other. So take, for instance, hydrogen and oxygen. Dalton thought that 1 gram of hydrogen would react with 7 grams of oxygen. So if those large laboratory piles of atoms had equivalent number of atoms, then the laboratory mass ratio should scale all the way down to the atomic level. So think about that. The relative mass of the atoms would be hydrogen 1 and oxygen 7. Take a look at the periodic table. Hydrogen's atomic mass is still right around 1. Dalton made a lot of mistakes for sure. If you look at the periodic table, the corrected relative masses are actually 1 to 16, not 1 to 7. But the big idea remains. We have an atomic mass in Daltons, and we have a laboratory mass in grams. It's the same number. It's the same reason why gold can be 19.3 grams per milliliter and 19.3 kilograms per liter. It's because the top and the bottom scale up by the same number, 1,000, so the ratio doesn't change. The number that connected those two realms of existence wasn't 1,000. It was astronomically larger. It was secret number N. But since it wasn't a direct part of the relationship, since it canceled out, scientists were doing just fine without knowing what secret number N really was. So if ratios aren't really your friend's thing, tell them that Avogadro never actually came up with Avogadro's number. In 1811, he was just an Italian physics professor with a different take on one of Gay-Lussac's discoveries. Gay-Lussac had noticed that when gases react together, they tend to do so in volumes which bear simple whole number ratios. Avogadro correctly took this to believe that equal volumes of any two gases under equal conditions contained equal numbers of molecules. Avogadro had a theory. He never had a number. The actual number of molecules in those equal volumes was unknowable and frankly irrelevant as long as they were identical, as long as there was the same number of molecules in each. Now, unfortunately, Avogadro's contributions were largely ignored during his lifetime for a variety of reasons. He might have been completely forgotten, save the efforts of a fellow Italian named Stanislao Canizzario. 4 years after Avogadro's death, Canizario would reintroduce the world to Avogadro's ideas in the waning hours of the world's first International Conference of Chemists, the extraordinary Karlsruhe Congress of 1860. Canizario used Avogadro's idea to lay out a convincing argument for what would become the basis of our current established relative atomic weights. People were impressed. One of those new devotees was none other than Dmitry Mendeleev, who, inspired by the strength of Canizario's advocacy of Avogadro's idea, would publish the first true periodic table within a decade. One of our biggest failures when we talk about secret number n is to leave out all the unique and clever techniques used throughout history to try to determine its value. There have been lots of them over the centuries, at least 6.02 times 10 to the 0.5. But this video isn't going to get into all of those attempts. There were lots of famous names along the way: Faraday, Millikan, Planck, Einstein. That's right, Einstein. It was the 20th century and we still hadn't definitively verified the existence of atoms. Think about it. Einstein had to take a break from his theories of relativity to help push this across the finish line. Finally, in 1909, Jean-Baptiste Perrin experimentally validated Einstein's theories. It involved an ultramicroscope and some tiny colloidal spheres, but in the end, he would finally have observable phenomenon that validated the existence of atoms. Perrin had 3 different experimental techniques that each independently validated very similar values for secret number n. After that, it became intellectually indefensible to further deny the existence of atoms, and this would earn him a Nobel Prize in Physics in 1926. Perrin, in a truly class act, recommended that the value of no longer secret number n be henceforth known as Avogadro's number, in tribute to his critical early contributions. So when you bring up Avogadro's number, discuss how scientists were using it long before they ever found it. Mull over the fact that Avogadro's number was the secret conversion between the atomic and the macroscopic realms of existence, and that the fate of the atomic theory of matter rested on its discovery. Heck, name drop Einstein if you have to, but don't spend your time on the number. Avogadro didn't know it, and you probably don't need to know it either. Unless, of course, it's also your anniversary. Thanks for watching, and have a great day.